In the deep of winter, you trek out in the snow to put up a trail camera, hoping to capture some great animal footage. Instead, when you come back to check, the batteries are dead and there are only a couple of videos. Welcome to the Windbury Wildlife Tech Series. Today I'll be covering the epic debug and repair of this Browning Recon Force Elite HP5 trail camera suffering from early battery drain in cold weather. Along the way, I'll give some general advice on how to debug this type of problem and some specific advice for this series of Browning trail cameras. In the end, this debug session went in a very unexpected, puzzling, and possibly unique direction. For those of you who can't wait, the problem turned out to be a faulty double EPROM. For those wanting to see how I got there, stay tuned. The owner of this camera wrote that it was eating batteries. It would go through a new set of alkaline and Energizer Ultimate Lithium batteries in about a week, all without capturing more than a handful of 30-second videos. He reported that the problem seemed to be associated with cold temperature, around minus 20 degrees Celsius or minus 4 degrees Fahrenheit. It was tempting to think of this as a cold battery problem. Alkaline batteries perform very poorly in these temperatures, but those of you who have read my post on trail camera batteries know that the Energizer Ultimate Lithium batteries perform very well, even at these frigid extremes. My first challenge was to reproduce the problem. We still had a bit of winter here in the northwest Montana, so I could have put the camera out in the yard, but I also needed to be able to instrument the camera while it was failing to figure out what was going on. That meant going and getting it to fail in the lab. I started by measuring the current drawn by the camera when idle, between video captures, and when actively taking daytime and nighttime video. I did this by connecting a power supply in series with my multimeter set to measure current. I measured about what I expected with this camera, 60 microamps in idle mode, about 120 milliamps for daytime video, and about 470 milliamps for nighttime video. All this with a power supply of about 12 volts. If the idle power had been higher, say in the range of tens of milliamps, it would point to something wrong with things kept on all the time in the camera. These include a low power MCU, the PIR sensor, and the charging circuit for the internal coin battery that keeps the real-time clock on. Or if the operating current without the flash had been high, I would suspect something wrong with the main SoC, possibly the main power converter. I ran the camera in the lab all night while taking periodic readings from my recording multimeter. Our cats helpfully obliged by creating several triggers at night. Looking at the data on a graph, the camera seemed to be working fine. It consumed very low power between videos and an expected level of power when triggered to take videos. All correct. On this particular camera, the measured power with the flash on at max power was about 10% higher than a known working reference camera. This is probably within the tolerance of the parts, but it made me wonder about the high current power supply for the IR LEDs. This power converter includes 2 electrolytic capacitors for filtering the switching power supply. These parts sometimes fail at extreme temperatures, so I decided to put them to the test. I put the disassembled camera into the freezer for several hours. You can see I put it in a Ziploc bag to prevent humidity from room temperature air from condensing on the circuit board when I take it out of the freezer. Then I powered the camera up in a diagnostic mode, which I cover in detail in a video linked in the description. In this mode, I was able to easily switch on and off the IR LEDs. After taking several thermal images and feeling the warm capacitors, I had almost convinced myself that I had found the problem. To double check, I squirted some freeze spray directly on the capacitors, hoping to see a sudden jump in current. There was none. Not the problem. For all my work, I hadn't really succeeded in reproducing the problem. That is, I couldn't find a case where the camera was consuming more power than it should. It's time to get serious. By now, the camera was open on the lab bench, and I had attached a set of leads to the serial test port located next to the SoC. I connected this port to a terminal emulator on my PC. I discovered this port while reverse engineering the firmware for these cameras. It spits out a lot of debug information from the SoC, including a message when the camera wakes up and when it goes back to sleep. Up until now, I had been powering the camera with my lab power supply set for 13 volts, which is about what I expect for a set of new EUL batteries. I decided to replicate the effects of cold batteries by reducing the voltage as I operated the camera. I gradually dialed down the voltage from 13 to 12 and lower while triggering the camera with my hand and watching the serial printout. At about 11.5 volts, something completely unexpected happened. The serial output suddenly complained of low battery voltage, the camera aborted the video, and it powered off. But then, less than a second later, it came back to life, again complaining of low battery power and again shutting off. And it kept repeating this pattern continuously, going on indefinitely, all the time consuming about 100 milliamps of current. In this state, it would not take any new videos. And at this rate, it would certainly have gone through a set of new EULs with a rated capacity of 3,000 milliamp hours in about 30 hours. From prior work on these cameras, I knew that they should operate at battery voltages well below 9 volts, which is obviously very much below 11.5 volts. And indeed, under very cold conditions, one might expect the voltage of even the EUL battery pack to drop below 11.5 volts while trying to power the IR flash at night. Aha! At least I had reproduced the problem. Now all I had to do was figure out what was going on. I now put the camera back in test mode and ran the verification test. These include a test of the voltage monitor for the battery. When I got to this test, the LCD display on the camera reported a battery voltage of 628.72 volts. Well, shoot. I wish I'd run this simple test earlier. I was getting much closer to the bug, as I knew that the actual voltage was closer to 12 volts and could never get anywhere near the hundreds of volts. My suspicions fell on the physical circuit that monitors the battery voltage. This because I knew that I was running the very same firmware on this camera and a reference camera, and the reference camera was reporting the correct voltage. I thought I was on to something when I measured different values for a small resistor, which I think is used as a resistor divider to bring the battery voltage into the range of voltage expected by the analog to digital converter on the SoC. But this turned out to be a red herring, brought about apparently by a change in the circuit board design between my older reference camera. The critical thing was that I measured the same voltage, about 2.0 volts, on the middle leg of the resistor divider, which is the right side of R111 on both cameras. This indicated that the problem was somehow in the SoC. I considered a failure of the analog to digital converter inside the SoC, but this seemed unlikely since the light sensor, which uses the same analog to digital converter, was working fine. I verified that the battery channel for the analog to digital converter was working in the broken camera by adding a quick diagnostic printout to my custom firmware for this camera. It reported that the raw values read from the battery voltage ADC channel was about 850, which was the same as reported from the working camera. What the heck? How was it that the two cameras with the same firmware were getting different results when converting the raw battery ADC value to an actual voltage? It was then that I noticed a subtle difference in the trace of the serial port between the two cameras as they booted up to take a video. The working camera reported "Volt-Calib bin file not found," whereas the failing camera had no such message. At this point, I used GDRA to dive deep into the firmware code for reading the battery voltage. After much trial and error, I found that if there is no calibration file available on the internal file system, the case for my working camera, the firmware would just use a default calibration setting to convert the raw ADC values to volts. However, if a Volt-Calib bin file existed, the firmware would load two calibration values from the file and use these to calculate the true battery voltage. This was what was happening in the failed camera. Unfortunately, the calibration values in the Volt-Calib.bin file were corrupted. This caused the conversion function to give wildly wrong answers, which caused the camera to think it was low on batteries, which caused it to go into an endless loop of waking up and going to sleep, consuming power, and so on, which caused the batteries to die. See? Simple. To fix this problem, all I needed to do was remove the Volt-Calib.bin file, or to overwrite it with the corrected data. But here's the thing. Every time I loaded new firmware into the camera, as I had done repeatedly in the debug process, I should have been erasing the Volt-Calib.bin file. This because the firmware image contains a complete copy of the internal file system, and this file system did not include a file called voltcal.bin, which could only mean one thing. Somehow, the double EPROM, which stores the firmware and the internal file system, had failed in a way that prevented the voltcal.bin file from being erased. In a previous video, I covered diagnosing and repairing the double EPROM in these cameras. Up until now, I had only seen double EPROM failures manifest by an inability to update camera settings or to install new firmware, both of which were working fine on this failed camera. Well, live and learn. I replaced the double EPROM and booted up in diagnostic mode. Here you can see the report, 13.72 volts. Thank goodness. I then verified that the camera now is operating fine with the battery voltages below 9 volts. A successful repair. Of course, there are still a couple of loose ends. I'm suspicious that this appears to be a case of an extremely unlikely double fault. That is, a file corrupted at the factory and then the double EPROM failing in just such a way that this file is not cleared. Replacing the double EPROM and in the process eliminating the corrupted voltcal.bin file fixed the problem, but I suspect we're not quite to the bottom of this bug. But I have other projects needing my attention, so we'll have to wait. Well, thanks for listening to this whole sordid story. If you'd like to see more long-form videos like this, please let me know in the comments below. Be sure to hit subscribe to see more content on camera trapping technology.